All right, there we go. So we're recording. And I'll make sure that everyone that's signed up will get a copy of this. We'll be going through a lot of different URLs and links to get through the mechanics of preparing to launch a high altitude balloon. There are other different projects you can run as well. This is really in light of the U.S. Department of Education's CTE mission CubeSat, but that's not a requirement, right? Obviously, you're planning for this mission. Maybe you're putting this together something that looks like this. You know, a satellite basically in a volume of a 10-centimeter cube. Your modern satellite, that's essentially what we've got there. And perhaps you've already got some electronics or you're building some of your own. We've got some of our own electronics that we use. You can visit and you can see that on our site. But I'm not really here to talk about our electronics today. I'm really more interested in sharing with you the process to prepare and launch a high altitude balloon. There are some FAA requirements we want to be cognizant of, and caution, of course, in planning is super important. So I'm going to make the assumption in this call right here, and by all means, please introduce yourselves in the chat, and if you have some questions, maybe pop it in as well, and I'll get to those in the back end of our hour. This assumption here is that you're already going through your engineering, and you've kind of got that figured out about what you want to fly and why you want to fly it. If we want to talk a little bit about payload, we can. If you'd like to talk something specific to the CTE mission CubeSat challenge, I can talk about that on the back end of this as well. But this call is really designed to take in place like, okay, I've got my CubeSat already built, I've got my electronics, I've got my means of communication. And so the key here is like, how are you going to actually get this aloft? It's going to take some planning. And we start, as in any case, of course, with the weather. Let me just, looks like my co-founder's here, Tony, so he's going to join us now. Just give it a second. I'm going to make him a co-host just in case I got something wrong. Hey, Tony.
Sorry, guys, I'm late.
That's okay. We're underway here.
I was on the other call.
Great. All right. So I'm going to make you a co-host, Tony. So we're getting underway right here. I've asked anyone to introduce themselves in chat, and this recorded session will be made available to you, as well as obviously all the links and some guides. But the most important thing right now with your mission is to think about, well, how are we going to fly this thing? So you're going to assume you've already got it built and you want to fly next month, right? Well, you're going to need to make some plans for that. And you're going to need to do some predictions. So I'm going to share my screen for the rest of this program, I think, for the most part, as we go through some of those dynamics of making those plans. All right, so hopefully everyone can see my screen here. I'll give it a second to make sure it pops up. Usually I like to start with a nice view of Earth. It's a simulated view, thanks to some really nice satellites in orbit and other things like other high altitude balloons and weather stations and buoys that are out there in the ocean, to give us a sense of what our Earth is doing in any point in time. This is essentially a simulation over the last 4 hours. This particular site, earth.nullschool.net, enables us to see that visual. And it's a really beautiful interactive screen. You can move the Earth around. Right now we're looking at wind patterns at surface level, ground level, mean sea level 0. But really we're going to send our balloon aloft. And so I do this just, if anything, just as impact and really getting a sense of what happens here. Of course, as you rise in altitude, your atmospheric pressure drops. With the lower pressure, you're going to see some different dynamics. Your balloon's going to be traveling as low as 250 hectopascals, or maybe even a little lower. And you can see the dynamics just now today over the last 4 hours. You can see that jet stream up north in Northern California, and Northern US. And it's really kind of moving pretty far across the country here. For your mid altitude balloons, when you're trying to circumnavigate the planet, this is super important to calculate. Of course, if you're going to be launching a high altitude balloon, in this case, I'll be running a simulation based on Berkeley, California. So you're really going to want to kind of drill in here and look at the dynamics of that local area. So that's what's kind of happening right over my head right now, about 20 miles in the atmosphere. And let's just go back down to the surface level again. And here's what the winds look like today at the surface level. Nice, calm afternoon to put something aloft. Your typical latex-filled high-altitude balloon is going to be aloft for about 3 hours, 2 hours up and about an hour down. So you need to take that into consideration. Of course, where it's going to go is super important because you want to get this thing back. You've invested perhaps months or maybe even a year or more in the design of your payload. You've got your radio comm set up. If you have questions about radios, we can talk about that at the back end of this, but it's really about planning for that flight, assuming you've got it all squared away. So this is just a great kind of visual start, but we're going to need to pull back from that, and we're going to need to look at what weather looks like. Maybe you're planning for something in January of next year or March or June or what have you. We want the students to actually do some predictions. So I've got another weather site here. You can pick any number of weather sites. I like Weather Underground for a couple different reasons I'm going to go over right now. One is it's got a history tab. And if you use the right ground station for your monitoring your weather, you can go back in history a decade or more. And so if you're saying I'm going to launch in March, there is no way you're going to predict what the weather is going to look like with the current stuff we have running right now. You're going to see maybe a week or 10 days into the future. But what your students can do, and if your students, what you can do is look historically at what's happened in the second week of March, last year, 2 years ago, 5 years ago, and you can start getting a sense of whether it may be good or not. You won't know until you actually get close. So I like this particular site because I can go back and look at history by picking a weather station that has some history. So that's a really great thing. And then I love the visualization. So here I'm looking at a forecast over the next 10 days. Absolutely fantastic. I've got a lot of information on the screen, and just maybe I'll make it a little larger if it's kind of hard to see. It's a little better. And of course, we've got days of the week. Here we are on Tuesday, this little visual about the clouds, highs and lows. But this is what I'm really interested in here is these graphs here where I've got temperature and I've got dew point here. If some predictions, you can see how it's changing over the week. It looks like it's warming up. You can see the diurnal cycles here. It's getting warmer and cooler in daytime and nighttime. And the graph down below, we've got cloud cover. That's not good. You need clear sky. FAA guidelines, 50% of that sky has got to be blue. You got to see the sky. Otherwise, you have to start worrying about interference with aviation. All right. So if I was going to launch right now, it's not going to be really good to do that, according to this. And of course, if I look at Wednesday, same thing. I've got some gaps here. So if I was going to make a plan and I said, hey, I'm going to launch this week, and I planned that 3 months ago, I'm looking at my weather now saying that's not going to happen. We now have to recalibrate. So rule number one, make plans. You get your whole school excited. You got the parents excited. Everyone's excited to do this. And the weather isn't participating, right? So you've got to make plans and expect that you're going to have to change. So that disappointment, if it's not planned for, is real. People get discouraged and you see the dwindling count of people wanting to show up. Let them know that there's a couple alternate dates for this, but it looks like it's going to be pretty good if you've done your predictions properly. Other things, of course, chance of precipitation. And down below, what I like most about this graph is it shows me wind speed and wind direction by the hour. Now, of course, it's a prediction, but this gives me a real clear indication here that if I'm going to launch in the afternoons here, and I kind of know that just because I live in the area, but the winds jump up and get really high. And I think that's the reason why people love to sail in the San Francisco Bay, because there's really great wind in the afternoon coming through the gate, and your sailboat, well, those sails will be nice filled and you're going to be moving across the water pretty well. So it's going to be calmer in the morning. And all of these seem pretty high here as we're getting up in speeds. This week, maybe not the best week unless I'm talking about like a dawn launch for this particular example. But for now, let's just assume that all works well. So I've kind of done an overview here looking at the Earth and what might be happening over the last few hours. One thing about the earth.nullschool.net is I can actually jump forward here 4-hour increments or even a full day up to about a week and back. There's other things you can model, you can play with as well, looking at not just surface and different atmospheric pressures, but changes in relative humidity, things like pollution. You've got things like particulates in the air or what have you. That's a fun one, just looking at particulates and pull back. And you can see the dusts from the Sahara kind of coming over to here to Central America. Look at that. And this again is at, this is, wait, let me do PM 10, there you go. This is a great visualizer and I think a wonderful conversation starter as your students, and this is, maybe you're just starting in the planning stage. What instrument do you want to put on your payload? Great place to start. So again, we went to the weather, kind of looking like, hey, we're just about ready to go. What does it look like? Maybe if it's far in the future, we've used this history model. And again, I have a preference for whether underground, but there's a lot of different services you can use. Then what do you do? Well, briefly, I want to introduce Magnitude, our company. We have a number of lessons that are built right into the browser. You can actually program an Arduino microcontroller through a Chromebook if you had some concerns about that. So we've looked at affordability and low cost for instrumentation. And we have a number of lessons that are in our catalog as well. I'm just going to briefly show this with you. And what I think we may do for those that are interested is open up a little trial where you can kind of see what this looks like and see if it meets your needs for your classroom experience. This is my more of a executive view here, but I'm pulling up our lesson library right now. We have lessons. They'll show 6th to 8th grade bands in here. These are easily adaptable for younger students and of course for our high school and university as well. We cover very specific instruments like acceleration, pressure, temperature. These are all lessons that you can involve yourself with if it's not just engineering practice. But what I wanted to show you here is just preparation for balloon launch. This is more of the mechanics to getting ready. Your launch date I've kind of just talked about, up to 7 days in the future. And what we're going to step to right now is actually using something called Hub, High Altitude Balloon Hub, is what it stands for. And we're going to run some prediction modeling. We'll run through that and measuring the time and what have you. But we'll walk through that. I just wanted to share our platform and let you know we do a number of things both terrestrially here in the upper atmosphere as well as in orbit. We run projects aboard the International Space Station, and we run projects at least once a year. We've got the next one coming up in February, in which we're looking at growing plants in microgravity for a number of reasons. But I won't go into that other than say if you're interested in science and space, check us out, Magnitude.io. So let's get back to the topic at hand, predictions. So again, I'm going to be launching from the Berkeley Marina under this simulation, and I've gone to predict.habhub.org. Again, all these links will be shared, and the video will be shared with anyone that's registered. And I have it, what I can do is once I've moved it around the map to locate where I am, I can set my location by setting map. In this case, I've already pre-done that to make it a little easy for us to walk through an hour. And so here I am. I can zoom in a little bit maybe. And we can see I'm kind of right there in the Berkeley Marina, just due east of the Golden Gate Bridge. And all that wind coming in here, all those sailboats running around and having a great time. So I've got my latitude and longitude. Note that's in decimal. And sometimes they're asking for degrees, minutes, and seconds in the different calculators we're going to use. Our launch altitude in meters. For now, I won't put anything in there, but this might be just like 8 meters or something. That's pretty important when you're doing your calculations if you're in the mountains, because you're going to have a burst altitude that will occur, or burst time that will occur a little earlier, because you're going to be reaching that threshold of your latex balloon a lot faster. Launch time, note that it's in UTC, Universal Time, and I'm just going to move it up an hour since I set this a little while ago. So it's just about midnight UTC. So make sure you're calculating that. You've got the proper date and time. And this is as if I was going to launch it right now. And what I'm going to do is I'm going to show you that right now prediction, but I'm also going to jump forward to show you what happens when you just move it by a few hours or by a day or two. Our ascent rate, these are default settings. Note these are all in meters, both altitude and ascent and descent rates. These are reasonable defaults. It really is going to be dependent on your payload, and you're going to be getting into that engineering, thinking about the lift of your helium gas or your hydrogen gas in your latex balloon, the overall mass of your payload, and do those calculations. But 4 is a little aggressive, honestly, because we typically like to fly 2.5, 3 kilograms or so. And so our ascent rate's usually closer to, say, 4 or 4.5. I'll just put 4 in there for right now. Ascent rate, it's often that we get a burst altitude going above 30,000 meters or about 100,000 feet or so. And so I'm going to put in 31,000 as a calculated burst altitude. And the descent rate is going to be dependent on your recovery mechanism. And 99.9% of the time, that's going to be a parachute. You can go through parachute design if you want to. You can also just go out and get a pre-made parachute. I'm going to recommend a pretty industrial one. You've got this payload coming down at 19 miles, right? You really don't want it crashing into something. So having a nice flight certified parachute, pretty important. We can make some recommendations if you want. We'll do that offline for anyone that has an interest. Maybe you've got some recommendations of others that we can explore as well. But that's some interesting physics you can explore. I think that descent rate's okay for this particular prediction. So I'm going to go ahead and run it. And what predict.habhub does is it runs a model very similar to what we're looking at with earth.nullschool.net, using weather models to give us an idea. And this is an interesting flight here. It's really kind of squirrely. It's heading north here, ascending, climbing up. It hits burst altitude, and then we have a descent rate landing into the mountains. Wow. So there's some challenges here. Recovery, right? What if it actually lands in the delta, lands in the water? That's happened before. What if it lands in the mountains or the forest or something that's really kind of unrecoverable for any time being? Take that into account. If we're concerned at all that this is unrecoverable because maybe it's off limits territory, or maybe it's going into the ocean, we're going to need to change either our launch time or our launch date. And the students, you guys have an opportunity to play with these numbers to think about an opportune time. Often when we're like launching in the Central Valley of California, we get a straight shot down the valley. We're going to end up in an orchard or just an open field. That's like perfect. Less happy circumstances or what ends in the Sierra Nevadas or something else like that. And in some instances, we've had to do that due to the not having the luxury of time near the end of the school year, just before a break, that type of thing. And we've tried to do our best that we can. We've got a lot of stories to tell if you're interested about how we've adjusted that. But for now, let's just say, well, all right, this is what it looked like if I wanted to launch right now while we're talking. This is what that balloon would look like. About 3 hours from now, it would be on the ground. Of course, this is assuming you've got great tracking on it. We can talk about tracking. Satellite tracker is a great idea. If you're down in a ravine, if you've got an APRS radio or some other device that's tracking that's relying on line of sight communications, it's going to disappear. It'll disappear before you get down to a couple thousand feet, more than likely. It's ready to go. That satellite tracker that you can pick up at going to like an REI sports store, what have you, is a great way to ensure if you've got a view to the sky, there's a good chance you're going to see it. Sometimes they're glitchy, but 99% recovery chance when you've got a radio that you're tracking and something like a satellite tracker as well. But why don't I jump forward 2 days just for the heck of it? I have no idea what's going to happen. Let's say we're going to launch instead of Tuesday, we're going to launch on Thursday because that looks a little sketchy. We didn't want to go in the mountains there, and maybe it's going to go in the water. So let's see what happens to our weather. Wow, look at that. Complete change. And we might have seen that if we went back to our weather predictions. As you get T-minus 7 days to your launch, you want to be running these morning and evening, if not even more often, to really see, is this the right date? Is this the right time? And so we can see here, in this case, it's almost a due east travel. We get over those mountains, we get out into the Central Valley, and boom, that's going to be a fun recovery out there in the countryside. It's probably going to be out in an open field somewhere. It's a courtesy call. You might want to contact the county sheriff, letting you know you're going to launch a balloon, in addition to contacting the FAA, which we'll cover in a minute. But it's always good to communicate with the community of where that balloon's going to go. And of course, you're going to be contacting the FAA because of the stuff in the sky, right? So that's really great. But here's some other interesting things you can do. What if you had a lighter payload or a heavier payload or a bigger or smaller parachute? So these calculations can be done right here. All right, I've got a super light payload. I'm going to send it 6 meters per second. And I've got a really super oversized parachute, and I'm just going to drift. I'm going to come down really nice and graceful. How far can I go? I'll run that prediction on that same day. It's going to extend out a little bit further, not too much, a little further east. But you can see as we adjust these things, and different days and different times of year are going to give you different results. So when you do your weigh-in, before you do all this, you've got your payload built and ready to go. You're going to know it weighs 2.5 kilograms or whatever, and you know how much helium you're using. You can start running these estimates. If you really want to get into advanced calculations, you can use the burst calculator right here, entering in some standard size balloons by standard manufacturers with other calculations as well, talking about here, we can go in densities and what have you of gases and making those adjustments if you're into the physics, the chemistry, or the sciences beyond engineering. We're not going to cover that today, but just figure that's an open area for exploration. All right, so we've looked at the weather. We've kind of done a high overview with the Earth.null school map. We've looked at something like weather underground to give us a 10-day forecast. We've then gone into some modeling about what our balloon's going to do. If you're going to plan on running something like a mid-altitude balloon and go for distance, that's a different beast. We can cover that at the very back end if anyone's interested. We're attempting a circumnavigation, just so you know, with something that just weighs 12 grams coming up here, probably closer to Halloween, maybe in early November. Right now, we're still trying to figure that out. And that's around the world balloon activity. Anyone can join in. And there's some fun activities around that. But this is a latex filled balloon. It's going to expand with the atmosphere and burst. With the limitations that the FAA puts in payloads, up to 7 pounds or so, we like to keep it under 5 pounds. Again, this thing's falling from the sky. Let's hope you've done everything correct so it's under parachute. But if anything should happen, you've got something pretty serious coming down. You want to make sure you're predicted. Companies like Magnitude, we carry insurance for this type of thing. I'm going to guess your school district or school probably will. The probability of actually landing in an urban area is low if you've done your modeling properly, and the chance it's going to impact anything on the ground is actually surprisingly low. With over 75 balloons under our belt, we've been in an urban area twice, and both of those were pretty much in an open area, again, because of planning. More often than not, we're out in the wilderness somewhere, working with the cows and the forest in some cases to try to get our balloon back. All right, so how do we do this with the FAA? Now, this is the rub. Filing a notice to airmen is a courtesy, and I highly recommend it. In addition to filing a notice to airmen, which is what I'm going to cover right now, the FAA requests 2 ways to bring your payload down. One is clearly the natural burst that's going to occur. But if you get a call from someone in the tower at some airport saying, take your balloon down right now, you better have those capabilities. And so there are different mechanical things and engineering designs you can do to either let the gas out, the burst, or separate your payload from the helium or hydrogen balloon. But that is a requirement. You can look up your FAR guidelines. I can forward that again in the email response to everyone that's signed up for this particular session. With that, we have to think about air traffic. I just said I'm going to launch from the urban core here. I've got Oakland International Airport. I've got San Francisco International. I have San Jose. We've been able to successfully launch in the San Francisco Bay Area because we communicate, right? You may be out in a rural area somewhere, small little regional airport. It behooves you to contact the FAA and file your notice to airmen. So what will that entail? Well, it will entail actually kind of figuring out where you are on the planet. And this is Sky Vector. This is really, I went out way too far. Oh no. All right, here we go. But this is pretty much your roads in the sky. These are typical flight paths, right? And you'll also notice there are beacons, radial beacons that will give a pilot an opportunity to know where they are in relation to everything else. And they do all their navigation based on these navigational aids. And they want to know the mean radial distance and the orientation of your balloon to that navigational aid, because as that pilot's flying that jetliner or that little twin engine plane, they're going to want to know where they are in relation to that navigational aid and where your balloon is in relation to that, because they will not always see visual. One thing I will point out is you do want a radar reflector. Really simple, easy thing that you can create as a nice little maker project. Think about like a 5 or 6 inch diameter intersection, 3 different circles that intersect each other. Little engineering challenge on how you make that work. You can cover it with aluminum foil. You want to make it lightweight. Does a reasonable job. You can go out and buy a professional radar reflector like you might find on a boat, but save yourself some money and just kind of build your own as a visual aid and navigational aid for the pilots. But in this case, we're going to be looking at navigational aids for this exercise. I'll be using Oakland International Airport, and let me just try to zoom in a little bit. It's kind of not really behaving very well. I got too many things open. And so here for Oakland, you can see that the call sign OAK. And also what's nice here, I've got the latitude and longitude, all right? I also have, if we go back and look at this predict.habhub, I also have the latitude and longitude of my launch location. So I have 2 points on this sphere on Earth. I need now to know the distance between those points, between the navigational aid and between our launch location. It's not a straight line, right? In the airplane, you're traveling over the surface of the Earth at a given altitude. So we need to find the mean radial distance. You can calculate that if you want to get into mathematics, but there's some calculators that'll make it a lot easier. So on SkyVector, we knew where we were. We found our navigational aid. We know the latitude and longitude of that. Now, what I'm going to need to do, because the predict.habhub has it in degree in decimal, but the calculator I'm going to need to use for mean radial distance is in degrees, minutes, and seconds. So I needed to run a conversion. This is just the FCC has a conversion calculator here. If I'm starting with DMS, I can convert to decimal. And if I've got decimal, I can convert to DMS. So in this case, I've converted our digital or decimal to degrees, minutes, and seconds. And then I can run a little calculator. In this case, this is for movable type in the UK. And you can see I've already plotted this, but from location, latitude and longitude of our launch location and our navigational aid, we are 17.5 kilometers roughly, bearing 333 degrees, and we even have a midpoint there. This is numbers and information you're going to want to write down. Then this is for your FAA call. And I'm going to actually give you a number now to file your notice to Airmen, and I'll put this in the correspondence as well. And Tony, maybe you can pop this into chat. It's 1877
1877
487
487
6867.
6867.
Right. And what you're going to do is you're going to call, and you're basically getting air traffic. It's going to tell you what state are you filing a notice for. You can say whatever state you're in. In this case, I'm saying California, and they're going to ask for more definition, northern or southern. I'm going to say Northern California. I'm on standby until I actually get someone to assist me. It only takes a minute or two, but you will get someone that pops on, and they answer. They're very friendly and helpful. If you don't have all your information, I recommend that you do have it and you stay professional. Introduce yourselves as a student work that you plan on launching a high altitude balloon, and they're going to ask for some information. So you want to give them Zulu time or the UTC or GMT time of your launch and date, so they know when it's going to happen. That's the first thing. And they're also going to want to know where you're going to be launching from. Of course, you already have your latitude and longitude. They'll want it in DMS, in degrees, minutes, and seconds, okay? And then they're going to ask you, since you've already done your homework, do you have the nearest navigational aid? Lo and behold, you've already done your homework and say, yes, I already have it. Now, if you fumble with it or you're confused or not sure which one, they're quite often, I'd say 95% of the time, very friendly and will take an extra time to walk you through that if needed. But you should do your homework, because they will be grateful, and I think you will be as well, in terms of learning this experience. And so they know where you're located, where you're launching from, they know the time, they know your distance to the navigational aid, and they're going to ask you some other questions. How high is this balloon going to go? And there's a certain point, but I think more than often, you can just say unlimited, and they're okay with that. They'll ask for how long would you like this window to be open. If you're planning for a 3-hour flight, give yourself 4, 5, or even 6 hours, because you might launch late. And this, when they file that notice to Airmen, if you're going to get in your little twin engine and go flying somewhere for vacation, you pull up all the NoTAMs and you can see this balloon looks like it's going to go up sometime this morning. And so they're going to be on the lookout for that, and they see the course that you're going to be traveling in, and they're aware of it. That's really just being courteous, right? And I think that's super important. Once you've done that, they're going to, they might have some additional questions. They may ask your predicted landing zone. And of course, since we've already run the predict.habhub, we can let them know, hey, it looks like it's going to be just due north of Linden, and we can give them an estimated landing time. If you actually look at the predict, it says it looks like we're going to be, flight time is 3 hours and 20 minutes. Just for safety, you might say 4 hours aloft in this particular instance, 3.5 hours. And they're going to be comfortable. They might have additional questions. They're going to ask for a contact number and the person that's responsible. I have had a call. It isn't that frequent. Out of the 70 some odd flights we've done, I think I've been called 3 times. And one time we got called from the air traffic control at LAX. We were launching due south of them, and we were already in the air, and they're saying, don't launch. And I said, dude, you already gave us the clearance. We're in the air. What should we do? I showed them where we were on the course. We had a radio we were tracking. He could see it. And he said, okay, it looks like you're all right. So we didn't have to pull it down. I would have had a lot of Boy Scouts disappointed in that particular day. So there you have it. So just having your information to them, they can contact you if there are any challenges, or they just need to make a correction. Sometimes they'll make an error in the filing, and they need to contact you to make that correction. You will get a designation. a NoTAM number, you can actually look it up on the FAA and print it out. You can see that you now have a notice to airmen. And that's usually, if you watch any of our videos, we have a YouTube channel, Magnitude.io. There's no dot in that, so youtube.com/Magnitude.io. You can see all the different balloon launches. And if everyone's cheering, if you're not watching the sound, that's probably because we just filed the notice to airmen. And it really feels like a sense of accomplishment because the team knows that their payload's done, and they're probably within 48 hours of this launch. That's one thing I didn't mention. You're going to be probably T-minus 48 hours to make this call, maybe 24 hours. You could do it like within 6 hours, but I'm recommending about a day. And because of the weather and changes, you don't want to make a call 3 days out because you might need to change it unless you're really absolutely sure. Beyond 3 days, they usually just say, can you call me back later? That's a little too far out. All right. Let me see if I should pause right here and see what questions people have. So are there any questions in chat? Or, it's a small enough group, you can just unmute your mic and I can take some questions here. And there's some other things we can talk about it as well. I'm moving a little fast. It all's recorded and we'll share it with you. But any questions from a group joining us today?
I noticed that Dwayne is now on the call.
Oh, awesome.
Yeah.
Good to see you, Dwayne. Now, I should mention, since he's here, I don't know if Professor Twiggs is here.
Hi.
Hey, Dwayne. The co-inventor of the modern satellite, Professor Bob Twiggs, will be joining us on Thursday. And we're going to be getting a little more into the engineering and the hardware. And Dwayne has actually got a deep space satellite going out. So he's well past the atmosphere at this point. So this challenge, the CTE mission CubeSat, is to get us excited. Really, it's about writing that proposal and getting an approval. But I'm under the assumption that if you're starting this, you might as well go all the way. Get something in the sky. You might work with a local rocket club and do some rocketry. You're going to need a pretty big airframe if it's a CubeSat. So a 6-inch airframe, just barely squeeze that in there. You're probably going to need a flight clearance of a rocket that size of maybe 10, 12, or 15,000 feet. Work with your local rocket club. They already file those notices to the NoTAMs and the FAA for clearance. A lot easier to do it that way. And then, of course, our balloons, really, for the most part, you can do them just about anywhere in the US. Different countries have different restrictions. I know that in South Africa, for example, it's next to impossible. It's not impossible, but it really next to impossible. In Germany, another example, you actually have to contact each state as it goes across. And those states aren't as big as the US states. And so you might have to call 2 or 3 different organizations to get approval. And, you get 2 approvals, but you didn't get approval in the middle where you're not flying anything, right? So a little more troublesome. Here in the US, much more reasonable. Our states are also larger, so it's unlikely you're going to cross any state boundaries. But it's the Federal Aviation Administration, not a state aviation that we're contacting. So if you launch it in California, it goes in Nevada, or it goes in Arizona, up to Oregon, not an issue, or wherever you might be. Yeah, so let's see. Questions, though, seriously, I want to open up here for you guys. If this is, you're ready to fly or you're just getting started, I'd like to hear where you are. Another thing, in addition to Dwayne and Professor Twiggs meeting on Thursday, on next Tuesday, we're going to do a little more kind of homework and look through proposals for this federal, Department of Education proposal, and look at those 5 components and really double check to make sure you've got everything squared away. We can't probably help you fill out any questions you have, but we'll give you an orientation about what we think are going to be your primary concerns in that rubric. But for now, just want to kind of talk a little bit about those balloons. So any questions? There must be some questions for someone. Is everyone excited about this? And it looks like Michelle from Oklahoma, I talk really fast, so you guys are gonna have to jump in and cut me off, is working with 6th grade, which is fabulous. A little on the younger side, but I think that's okay if you take your time. We've worked with students in primary school. Most of our work is done in middle school at a minimum, usually 7th or 8th grade, and of course, high schools and universities. In fact, our first launch was with UC Berkeley, which was a lot of fun. I will mention, as an alternative to the larger high altitude balloons, the mid altitude balloons are a heck of a lot of fun. I just got a few more in stock here. There is a NASA engineer down in Huntsville, Bill Brown, And he's been building payloads for balloons for about 30 years. And he has a wonderful little device called the Sky Tracker. I'll just show you. So unlike what you might be developing here, this is the entire device. And unfortunately, it's not a kit. You can't solder it together and engineer it. He programs it and puts everything in there. And I think Professor Twiggs's ears are burning because he's coming in right now. We'll say hi to Bob. But you can see we've got our solar panels. It's solar powered. It only weighs about 12 grams. It's got a GPS for location, temperature, and humidity. And we're using an amateur radio for communications. These long guitar strings, literally, are our antenna to transmit. So these things only transmit during the day. But get this, we fly them on Mylar party balloons, just 1 meter in diameter, or super pressure balloons is an alternative. They're underfilled. They'll reach their float altitude. And unlike the latex balloons that we fly the big payloads on, like you're going to fly your CubeSat, these will get up around, well, depending on the balloon you're using, maybe 25 or 30,000 feet or 45,000 feet, and they just go. So I'll show you here. This is, we haven't quite gone around the world yet, but earlier during the pandemic, we want to keep our students engaged and our teachers inspired and give them a little relief from the craziness that we're dealing with this pandemic stuff. But I'll just share this screen here just because it's just so much fun. This is a flight nearly around the world. And unfortunately, it only tracks 7 days. So we launched here in Berkeley, went all the way across the US. It popped up on the eastern seaboard, and you can see the straight line is when we didn't get any radio communications at all. We're running just a 2 meter radio on this. And if I had a 30 meter radio license, which I don't have a general, just a technician, we could probably pick up that signal over the ocean, which would have been pretty awesome during the day. But what's cool is off the coast of Africa, it woke up. And how exciting that was for all our students as this thing's going around the world. It made it across the Atlantic, disappeared again for a day or so, and it popped over just over Egypt and got quiet. And a few days later, it woke up over just over eastern China, and it actually went right over Pyongyang, right through North Korea. We lost it in the Japan Sea on the way to Japan. So these little payloads I just shared with you, and the reason why I brought it up is I saw that a teacher there from teaching sixth graders talk about inspiration. It's a multidisciplinary, a transdisciplinary approach to learning. You can talk about history, geography, current affairs as this balloon goes around the world. If you want to join us in that, send me a quick little note or put something in the chat. I'll make sure I send you information about our around the world balloon launches is coming up probably in the next 4 to 6 weeks. I'm still working out the date on that. There's a lot of crazy starts to this school year. But a seat on that mission is $1 a kid. So it's just $1 and to talk about a field trip, right? And it's a lot of fun. Now, there's not a lot of engineering. In fact, there's none, but they can do predictions, just like we're looking with our big balloon and other things as well. So super fun. And who knows, maybe they're part of a team that we're able to get and go around the world. I guess one other thing, and since Bob, you're here, I want you to chat a little bit with these folks. I do want to mention that a really well-respected engineer over at Moorhead State just released the Cubesat Handbook. It's a text it's really designed for university. It's great for you as educators if you want to make sure you're covering all the different domains of your CubeSat. And Elsevier is the publisher. It's expensive. It's a couple $100. But the Cubesat Handbook, if you look it up, it's from mission design to operations. It's not really talking about these balloons, it's about terrestrial. It's talking about what Dwayne and Professor Twiggs have done, getting something into orbit and even beyond orbit. So Professor and Dwayne, since we've got you here, why don't you just do a quick intro and perhaps lead us with some inspiration as we talk about taking our prototypes, lofting them up into the stratosphere with high altitude balloons.
Well, thanks. I really wanted to jump in when somebody asked about sixth graders. So I'm Dwayne Cecil. I'm the former chief scientist of NASA's Applied Sciences program. And I worked for all 3 of the U.S. space agencies, U.S. Geological Survey with Landsat, NASA, and NOAA. And I'm a climate scientist. And so our programs headquartered here in North Carolina, Western North Carolina, are focused on weather and climate observations. And I just want to comment, there was a question about sixth graders. We had a launch from NASA's Wallops Island facility on April 17th last year on a Northrop Grumman supply rocket headed for a space station. And on that, and Bob can tell you more about it because this was all Bob's idea. On that rocket, there were about 60 schools represented from across the United States. And part of our North Carolina team included 3 elementary schools in Kentucky on a satellite launch, satellite that they designed the experiments for. And it all started with balloons, with tethered balloons in phase 1, tethered balloons and low altitude balloons, phase 2, high altitude balloons, and then phase 3 was the launch on the supply rocket. And so balloons are a great place to start. And we start all of our programs with balloons, from our space camp to our deep space mission that we're flying on Artemis 1. So it's great that you're here and that you're hearing. These guys are the balloon guys. I mean, we do it as a step in what we do, but it all starts with balloons. So, Bob, you want to jump in?
Yeah, that's. I think it's really important for these programs to start out simple and allow enough time to to learn what's going on rather than jump right into a CubeSat from the very beginning. And I do believe that that these balloons are just a tremendous thing to do. Even if you just have a tethered balloon, you're getting a lot of the things that you would with learning with a satellite. And my feeling with these CubeSat programs that 90 or 95% of the learning occurs before the satellite goes out the door to be launched. And so that's why it's important to not get too anxious about getting a CubeSat launched, but learn all the steps in between. And I think if there's any thing that we should pass on to the schools, that would be it. Magnitude they've done a terrific job. They've done a lot of great things, and I think that we have a chance now to help a lot of schools that may not normally do a CubeSat program. There have been so many schools that have started CubeSat programs and never got a CubeSat launched, and they felt that was a failure, and that's really not the case. So I even though the motivation is to get a satellite in space, which is a cool thing, there's so much learning that goes on before you ever do that, and I think that's and the thing of it is to get a CubeSat in space is an expensive, difficult situation now. It is a lot of work, and there's a lot of paperwork that goes on. We have to go through a number of agencies. So I think that we can do an awful lot of things by encouraging the schools to do things with balloons, and a lot cheaper. The kind of devices that we use to fly at those altitudes is quite a bit different than what we have to do to fly in a CubeSat.
So I'm on mute. You're not going to hear me if I'm
Yeah.
Dwayne and Bob, maybe talk a little about radio. Communication is super important. I kind of glossed that over because I wanted to walk through the mechanics of preparing for a flight, what we use, the different calculations to see what's aloft and how to recover it. But without radio communications, we got nothing, right? And so quite often we'll just go out and get a satellite tracker, just something inexpensive you can get at the hobby store, the sports store. But the ham radio, the amateur radio is usually what we carry aloft as well. That same amateur radio band can be used on your satellites as well, right? And so maybe talk a little bit about the importance of radio communications for any of these operations, whether we're here on Earth, a flat sat, just in the classroom, or a tethered balloon, or even sending something aloft. And of course, for your satellites, ground stations, I think, are also important. Our system here at Magnitude, with just an Arduino microcontroller and some simple electronics, also includes essentially a Chromebook that you convert to a ground station. But can you guys talk a little bit maybe about communications and how important it is once you've sent that aloft?
To me, our team is made. Bob's the technical expert on our team, and I'm the science application side of the house. Even though I'm an engineer, I really focus on the science applications, and that's the so what. So you've designed these platforms, you've come up with a remote sensing program, you're flying it either on a tethered balloon or a free flying balloon, and you need to get those data back, and you get those data back, then that's where the science comes in. It's extremely important. I mean, you can prove on the bench, you can prove in your laboratory, in your schoolroom, that you can design and build these remote sensing platforms, but you have to be able to communicate with them. And once you get the data back, that's really the so what of these programs. So you designed this, you flew it for a reason. Why did you design your remote sensing platform, and what was the goal? And the data from that remote sensing platform is that's what you're after. And so you must communicate with it. And Bob can tell you there's several ways that we do that.
Right, yeah. Initially we started with a CubeSat program because a lot of us had had ham radio experience and had built amateur radio satellites. We counted very heavily on using the ham radio bands, the UHF and the VHF bands. There's some procedures you have to go through to do that. There are a lot of people around now that are using those on the education side. It's not it's not a high speed system, and you only get communication for anywhere from 5 to 15 minutes when it comes over the top of you. And a LEO satellite has got about a 90-minute orbit, and so you'll see it twice a day, and maybe each time it gets over you, you'll have a couple of passes to communicate, and 12 hours later, so you get another couple of passes. So it's difficult to get very much data down, but there's some new technology that's come along that changes that. There's a couple of satellite constellations that are up there called Iridium and Global Star, and they now have permission to fly these little radios on the Global Star and the Iridium on satellites. And the advantage to that is that you get worldwide coverage on it. Any place that the global communication works. And with the Iridium, it's pretty well the whole globe. The Global Star has some limitations at the higher latitudes, but there is a limitation on that, and the limitation is the data rate. There's not a very high data rate on it, but if you can get some data back all the way around the world and continuously, that's pretty cool. Now, these are new radios that have just come about using them in satellites, although the Global Star and the Iridium has been around for quite a few years. They've just got permission to use them on the satellites, and they're really pretty good. They could also be used on the balloons, and so you could get coverage while it's over the ocean on a balloon with these radios, and they're not terribly expensive. You can buy a Global Star radio that can fit in fly on a balloon. It's only several $100s, but one of the things you do is you do pay for the use of it. So it's like a subscription service. The other thing that's coming along that we might see pretty soon, and I don't know when they'll let us do it, is the Starlink constellation that SpaceX is putting up, and that has some real ramifications in terms of data rate and everything else. So maybe over the next 5 years you're going to see some real changes. But the two things that we really have now are the UHF and the VHF radios, and Global Star and Iridium. So they're options there, as well as you can't use the amateur radios in the CubeSats. You've got that has to be a little differently than flying them in the balloons, because you've got one of the things, if you fly a radio in a CubeSat, if they don't like what you're doing with it or the frequency you're using, you have to have an ability to shut it down. So it can't be a transmit only. it's a little bit different when you're flying a balloon. You have a little bit more latitude there, but the communication is there, and it's improved an awful lot over the last 10 years. And they are making CubeSat radios now that are much higher data rate, but they're pretty expensive also.
I'd like to add a couple quick things. Before we even get to space, in these training programs with our students, they build small ground stations for receiving the data, and these plug right into their notebook computers. And they build the stations, they plug them into their computers, and they communicate with weather stations they build that are in their backyard, weather stations that they build that they put on rovers that they build and program, learn to build and program the rovers. So now we've got a mobile weather station. They've got a stationary weather station in their backyard, and we have a weather station on the balloon, a weather platform on the balloon. And so all of those are communicating with their ground stations. And so they're looking at through the atmospheric column of weather parameters. And so the communications, all of that is really important, but it's a ground station that they use to collect the data with small with receivers from all these platforms, and plug then directly right into their data analytics that we help them develop. And a lot of it's just off the shelf data analytics, but then they get some immediate return on, and they can graphically see the data and start understanding what's going on in the atmosphere. So the communication is key to all of that.
Wonderful. Thank you, Dwayne. And Tony, it looks like answered George's question a little bit. Yeah, it does get really cold up there. One thing that we expect the students to do, in addition to the weather modeling and prediction, is to think about the layers of the atmosphere and how that temperature and radiation and pressure and what's happening as you move up there. And that's ripe for investigation. You know, I like what you say, Bob, is what if there are little bugs up there, right? Can you create some kind of device that actually sucks up some of the atmosphere that when you recover it, maybe you have something under the microscope that you can see that you didn't see here on Earth. Of course, setting that up to be clean and not, what am I thinking of? Not contaminated by what you did on the ground. Super important. But it does get very cold. Expect more than a -40 C in many instances. The batteries that you choose are really important. You can't just put alkalines in here. The chemistry of an alkaline cell will stop functioning in those kind of cold temperatures. So just like your mission to send something in orbit, you're going to do vibration testing. You're going to do temperature testing. You might even do radiation testing. What do they call it, Bob? Shake and bake? Right. Do a little shake and bake to make sure it works. And so you might do that even if you're going to put something just in a high altitude balloon. You get up into the stratosphere, you get up above the ozone layer. Man, that's a pretty hostile environment. What can you do to maintain your electronics? What's interesting, your radios, since they're generating heat, usually stay up, but your electronics might shut down depending on how you've set it up. So as Tony's mentioned here, sometimes we just go out and get pocket warmers, throw a couple of those in there, adds a little bit to the weight, super inexpensive, low cost solution. But back to the ground station. So with our electronics that you just basically fit on top of an Arduino, didn't really run through them real quick, but so here's the inside of a CubeSat. We have them actually, and Bob, your original invention, the CanSat, is what we normally have them in. And let me just disconnect this here real quick. So this is your Arduino microcontroller. You can get pretty much anywhere for 20 bucks or so, 25 bucks. And here's what our electronics look like.
You get them cheaper in China if somebody wants to go there.
It's not really an Arduino per se, right? It's an Arduino
we won't
design.
say that. I won't tell you that it's cheaper than a Burger King.
There you go. Okay. Might be the same color, but it's not actually an Arduino. So actually Arduino will be more expensive. But on this, actually I have another shield. I'll just take this off real quick, which is a radio. What we've opted to use is a non-license required radio, just the XBs. And for the balloons, we use the Pro, which is, it tells us we get a range of about 28 miles, which is good for your initial launch, maybe for the first 30 minutes or an hour or so. We had one launch in Michigan, northern Michigan, and it was right next to the airport. Of course, we had to do all our FAA stuff. It went aloft and it pretty much spiraled up around the airport. And we had contact with it for the first hour and 15 minutes before it took off, which was really great. And we were able to get all that data and the telemetry down. So here's your ground station, just a little wire. And then we have an equivalent shield that you just put right on top of your Arduino, and then you connect it to a Yagi antenna. You connect that to something as simple as a Chromebook, and now you've got data visualization right there at the flight line. Your team has just sent this thing aloft. You're watching it go up. Your team has got that pointed towards your balloon, and you're getting all the telemetry, the temperature, the humidity, acceleration, magnetic fields, light levels, GPS location. All these things are on this little shield.
I'm putting up the data.
What's that?
I said I'm putting up the data.
Oh, there, share that.
Yep.
Yeah, so let me look at, are there other questions here in the group? I do have a hard stop at the top of the hour. We've got another session coming up in a different field, but I really welcome your questions if you have any now, and please keep them coming. Our hope, working and talking about this design challenge, is it's just not this design challenge, but students, teachers, we're hoping you're inspired to think about a multi-year, multidisciplinary program. We can help you work with folks like Professor Twiggs and Dwayne, or NASA, as the case may be, NOAA, your local school districts, Department of Ed, if they expand what they're doing. And, you know, if you have a 5-year plan, if you're an incoming freshman, it's a good chance on your college application, it could say, built and launched a satellite, right? Or built and designed a satellite and scheduled to launch in my senior year or my first year of college. And that's a differentiator, right? How many other students can say that?
Absolutely is, Ted.
And so
Big
plan for that. And do something simple and easy. I personally love simple and measurable. Do something that you know you can get done this school year, and then imagine what can you do next and build on that. What so often is when we work on the design side, we're imagining what we want to put in our payloads. The students come up with some really amazing ideas. They're like postgraduate work. Well, that's a great idea, but why don't we start with something simple to show that we can do it and work to that, because it's going to take a year or two or even longer to get that experiment underway. And what's disappointing is someone spends all that time and realizing that they're 40% of the way there, and this balloon's going up next week. So you have to really be prepared that some of your more ambitious projects will take some time. You can't shortcut that, that's for sure. So what are you doing here, Tony? You're loading up some data?
No, well, I have shown the data sets.
Okay.
What they can see when we are running it live.
Oh, there you go. So that's acceleration right there. That's great.
Yep.
And of course, all of this is captured in the cloud. So if you're doing flight, one thing I mentioned, our system has a data card on it. There are many different types of electronics you can use. Magnitude is just one organization. We're focused on learning. And so we built something that makes it easy to get right into the science. You know, it's like if you went to math class and they asked you to build a calculator before you could use it. Well, we just want you to do the calculations. We want you to get in and get that data, get into the science as a start. And then, my goodness, go in advanced class with Bob there, and you're going to be doing some breadboarding, some circuit design, building your own PCB. And that's, you know, the subsequent steps. But what we like to do is just get that win under our belts, have a sense of success, and your community. One of those aspects of this challenge here is engaging your community. You're probably going to want to do some fundraising. Typical balloon launch is going to be a couple $100. A lot of it's just for the helium and the balloon and a lot of time. But if you're really planning on putting something in orbit, a lot of time, and it's not cheap. Now you can probably find some discounted equipment or some lighter weight equipment or even conventional off-the-shelf components that can work. They have a reasonable technology readiness level. But for the most part, you're going to be in the tens of thousands of dollars at a minimum, plus your flight. There's something called the CubeSat, CSLI, CubeSat Launch Initiative, that NASA sponsors. It's going to be opening up, I think, in November of this year. And you can apply. You can submit an application to NASA, giving them the reasons why you think that they should give you a free ride to space. And they do that for high school students. They've done that for middle school students. I think 1 or 2 schools have done that. Usually it's universities. And of course, it's all just here in the United States, so you're not competing against other countries. So that's something that you should plan for, and also consider on your team. You have your engineers on your team, and you have your scientists on your team. You might have your media and PR folks that really love to do that. They love to do Instagram and Facebook or what have you, TikTok. And you're going to have those individuals that are really excited about those things. but you're also going to want to make sure you're covering all these other bases as well. So here we are at the top of the hour. I'm going to see if there's any other questions, but I'm going to have to sign out for today. And by all means, we'll share this link once it's compiled to everyone that's signed up. And in that, you should have all the links that you need. If you have any further questions, please send an email to hello@Magnitude.io. And on Thursday, same time, join us. I'll shut up, and you're going to get the chance to listen to the experts, Dwayne and Bob Twiggs, in which they're going to talk more about your entire mission. And then join us again next Tuesday when we just go through your 5 steps of the rubric to make sure you really got all nice and tight. I'm going to hope that everyone that's joining us today is going to be ambitious enough and puts the work in that you guys will be finalists. Really hope we can see that happen. None of us are judges, so we're open to helping you guys out. Let us know. If we were judging, we'd have to recuse ourselves, but we're free roaming right here. Feel free to reach out now and the deadline. And I hope well after that as well, if you're really ambitious and want to do something exciting. So guys, really looking forward to seeing what you guys come up with. Please share your experiences with us. We love to make sure other folks know about what people are doing around the world and here in the United States. So thanks for joining us today, and we'll catch up with you real soon. We'll see you in the stars.
Yep.
Have a good evening. Bye-bye.
Yep.